Thank you all for having me back today. It's a pleasure to be here. We've been looking forward to coming back today, and it's fun to see you. You may recall from our previous meeting this painting. It's of a famous collaboration that failed because the partners didn't speak each other's language. It's the Tower of Babel. And as we discussed last time, to make a collaboration really effective, it helps to have some understanding of each other's way of seeing things and of each other's language. And as before, that is the purpose of our talk today, is to share a little more of how certain researchers think about significance and the meaning of the data that are gathered in the course of doing a study. Today we're going to look at a few more graphs and numbers than we did last time. It shouldn't be too bad. Mostly we're going to be getting at the conceptual stuff, but there'll be a few more, a little bit of, it won't be too technical, but there will be a little more numbers and graphs in here. To truly understand the technical side of this, you really need a course in biostatistics, which isn't that tough. It's just that it's a little more than we can do in 45 minutes today. So, as before, I have a little disclaimer here. The following presentation will not make you into a statistician. But having said that, I want everyone to feel comfortable in asking a question, because some of this might either be new or it might be something you've had before and it's just not fresh. So I'd really like it if something is not registering to say, wait a second, I'd like to stop, because we can clarify it. Let's stop and make sure that it gets clear before we move on. But it's not going to be too bad. I'm pretty confident of that. So what I hope we will do today is renew your familiarity with a few basic research concepts and terms. I hope we'll introduce a few concepts and terms that are commonly used when researchers analyze and try to understand the data from their studies. And I hope that, as before, we'll provide a foundation on which you can build, and that may make it easier for you to work in partnership with academic researchers. So it's going back to that slide of looking inside the head, try to give you a little bit more of a glimpse of what's going inside the heads of your academic partners. So we are going to start by reviewing some basic terms and concepts, things that we talked about last time, but briefly. We talked about association. We're going to talk about a slightly different but equivalent term called correlation today. We are going to talk again about exposure and outcome and the relationship between these things. And we mentioned briefly these terms of independent and dependent variables, and we're going to go into a little more detail about how those two things are associated with exposure and outcome. And we'll very briefly go over study designs, mostly as the study designs are important for interpreting data. And so some of the new stuff we'll do today is talk about comparing groups, sampling from a population, and we'll talk about statistical significance. So here's a slide that should look familiar. We talked last time about association when two or more things are frequently found together, like Fred Astaire and Ginger Rogers. It's about a relationship, two things you grow accustomed to seeing together. Not always, but often. Another essentially equivalent term for association is correlation. There's some slight differences that aren't important for today, but essentially these things are the same. So last time you may recall we had an example where we talked about ice cream consumption and how it was associated with an increase in shark bites, and it was associated with an increase in boating accidents and increase in sunburn. And we talked about those associations not being causal. So it seemed a little strange at first. We thought, well, ice cream consumption doesn't really cause sunburn, but the two things come together because there's this other thing, a confounder called summertime. But we did talk about a presumed causal association or correlation between ice cream consumption and overweight. So we have a graph here, and the way to read this graph is to look at this axis or this line, and as this line goes from here in this direction, it indicates an increase in the average consumption of ice cream. And the other line, as we go from here up, indicates an increase in the percentage of people being overweight. So up higher is more overweight. So today we're going to talk a little bit more about the relationship between exposure and, or what we call an independent variable, and the outcome, or what we call a dependent variable. You may recall that last time we talked a little bit about exposure and outcome using kind of a medical models. And that's where these terms first started to arise. So the exposure might be to a germ or to some kind of an infectious agent, and the outcome would be the disease that came from that. But we also talked about the fact that an exposure and an outcome don't necessarily have to be disease and a germ and a disease as such. It could have to do with socioeconomic status, which could be an exposure, different kinds of things or outcomes that derive from that. So in review, an exposure is a state of contact with something or any relevant characteristic, a habit or a practice that may increase or decrease the likelihood of an outcome. We showed one where it increases, but it could also be associated with a decrease in an outcome. An outcome is the disease or other condition that results from the exposure.
Or lack thereof.
Or lack thereof. So, and this may be on your quiz, so-called. Paul wants me to call it a survey. But this idea of independent and dependent variable and how they relate to exposure and outcome. Here's a different example. Again, we have an exposure or an independent variable. In this case, we're looking at aerobic exercise. So someone whose average aerobic exercise is down on this side of the line would be doing less aerobic exercise than someone whose average aerobic exercise is on that side. The outcome, or the dependent variable, is cardiovascular fitness. So similarly, someone down here, lower level of cardiovascular fitness than someone up here. So what I want to try to show is the logic behind these terms of an independent and a dependent variable. And sometimes it's just a factor really, or a function of how you're setting the question up. So in this case, we're setting up a question which is, if a person gets more aerobic exercise, then does that have an effect on their cardiovascular fitness? So another way of phrasing it is that if one of the variables, in this case the independent variable, changes, does that mean that the other variable changes? So this one we change, and does it have an effect on that? This one is dependent on change in this. So let's see, here we have a level of aerobic exercise. And let's suppose that that level of aerobic exercise correlates with, or is associated with, this level of the dependent variable of cardiovascular fitness. We can plot those, the place where the two of them come together. A higher level of aerobic exercise and a higher level of cardiovascular fitness. A higher still level of aerobic exercise with a higher level of cardiovascular fitness. And I think you get the idea, you see the pattern. And eventually we get something we can make a little bit of sense out of, and we can draw a line through it. It starts to look a little similar to the previous graph where we saw a relationship where one variable, the aerobic exercise, the independent variable, increases, and cardiovascular fitness increasing along with it. So when we see a pattern like this where one variable increases, the associated variable also increases, something like this, we call it a positive correlation. This may be on your quiz, cum survey. Yeah. So a positive correlation is one in which the increase in one of the variables, the exposure or the independent variable, it results in an increase in the other variable or the outcome variable. We could see a situation like this, where an increase in aerobic exercise could be associated with a decrease in overweight. And in a situation like this, where an increase in the exposure variable results in a decrease in the outcome variable, is called a negative correlation. So they're still associated, there's still a correlation. It's just a matter of the way the two things relate to one another. Everybody's good with that concept?
Are you going to talk about what happens if they both go down?
No, we won't. We'll leave that to another day. Okay. That would be effectively a positive correlation, though, right? It's just a matter of how you configure it, because they're both going in the same direction. So.
But if we were applying the independent and dependent variable to what you heard us talk about today, what would those terms be?
What do you think? What does someone else think?
The independent variable would be the distribution of the pick of the month, and then the dependent would be green, and if that's what we were measuring.
Yeah, exactly. Yeah, so you're manipulating the pick of the month. That's your independent variable, and you're trying to see if a manipulation of that variable results in some other effect. So last time, you may remember, we talked about a variety of study types, and this is a list of the main quantitative study types we talked about. We talked a little bit about qualitative research as well. And we talked about the fact that these different study types, descriptive study, cross-sectional, case control, cohort, randomized trial, can be used to answer different questions under different circumstances. They all have their own advantages and disadvantages. There are some sorts of questions you really wouldn't use a certain study type for. There are others that you might use several for. You might make your decisions based upon your budget or your sample size, how much time you have. So we learned that these different study types have a lot of different characteristics. One thing they have in common or several things they have in common are 4 basic stages. So you start by posing a researchable question. That's what this group's working on this morning. You design a study to get data to answer that question. These 2 things in some ways are happening hand in hand with this group. You guys are working on your study design, you're tweaking it a little bit, your researchable question is starting to focus in a little. Once you have a protocol that's based on your study design, you gather some data, and then you analyze and interpret the data. And another thing that all of these study designs more or less have in common is that they compare one group with another. So they will be looking at an intervention group, the eye of the PICO, and comparing it to the comparator group. That's why we call it the comparator group. So I'd like to take this idea of comparing groups and start to explore some of the approaches that we use and the way that we think about designing groups that can be compared, and some of the issues that a statistician and someone designing a study needs to consider when trying to compare groups. So let's start with this question of which school has the taller 7th grade boys. So I put this talk together a couple of weeks ago. It was close to President's Day, so I figured Washington Junior High and Lincoln Junior High would be good schools to look at. So we're trying to figure out whether Washington or Lincoln Junior High has the taller 7th grade boys. So we go to do our study one day, and we go to the cafeteria at Washington Junior High, and the first 7th grade boy that comes out, we measure, and we get his consent and everything, IRB and all that. And then we measure him, and we find that he is 62 inches tall, 5 feet 2 inches. Later that week, we are over at Lincoln Junior High. We do a similar thing. First boy coming out, 7th grader, we measure 56 inches or 4 foot 8 inches. So based on this, we can make a conclusion that the 7th grade boys at Washington Junior High are taller than the 7th grade boys at Lincoln Junior High. We see that 62 inches tall at Washington and 56 inches tall at Lincoln Junior High. So are you convinced?
No.
Why not?
Small sample.
What do you mean?
You may have randomly gotten the tallest boy at that school and the shortest boy at that school. It doesn't tell you overall if they're one and one is too small.
Okay. Does anyone else agree with that objection? Okay. Any other concerns?
Well, on taller, you didn't define like the average height or on, so if they had some student who was 7 feet tall, but the rest of them are 4 feet tall, how's that going to balance out? Is the average height of the class, or is it?
Okay. Another good point. So what more do you want to know?
All the heights.
You want to know all the heights? Okay. Suppose you're studying. Suppose your question is, what is the average height, not of the 7th grade boys in Washington Junior High versus Lincoln Junior High, but suppose you want to know if the average height of 7th grade boys in Oregon is higher than that 7th grade boys in Washington. Do you still want to measure them all?
No, but you need a representative sample size.
Okay. So why don't you want to measure them all? Not practical, right? You're not going to. You're not going to be able. Even if you had the resources and had the time, you probably couldn't get them all measured. And that's an important point about what we're talking about today. Is this idea of sampling, getting a sample or a smaller portion of a larger group, and trying to make some conclusions about that larger group based on the smaller sample. The fancy word for this is inductive statistics. So the idea of induction is making a conclusion about something more general based on something more narrow. And that's if we could, it probably wouldn't be impractical in a situation like this to line up all the 7th grade boys in both schools and just measure them. We wouldn't need statistics. because we would know. We would know which is truly taller, presuming we measured accurately and reliably. But let's take this example then and expand it. Suppose I got the second boy in Washington Junior High who came out of the cafeteria that same day, and he's 54 inches tall. So this kind of is consistent with Melissa's conjecture that maybe we got a taller kid at that school. And the second kid who comes out of the cafeteria at Lincoln Junior High, 7th grade boy, 63 inches tall. So we can calculate a mean or an average. Mean is just another way of saying the average. And the average we would calculate by taking the sum or adding up all the heights of the boys who we measured and dividing that sum by the number of boys that we measured. So we would add 62 and 54, which we're doing here, and we would divide it by 2, which is the total number of boys that we measured. So 62 plus 54 is 116. We divide that by 2, and we find that the mean average at Washington Junior High, based on a sample of 2, is 58 inches. We do a similar kind of calculation for Lincoln Junior High, 59.5 inches. So now our conclusion kind of reverses. It looks like Lincoln Junior High is a little taller. So let's assume there's 100 7th grade boys in each of these schools, and we sampled 35 from each. So now we've got a sample of 35. We found that the mean at Washington, same sort of a process. We take the sum of the heights of all 35 of those boys, we divide it by 35, 58.3 inches. Similar process at Lincoln, 58.1. They're starting to look a little more similar. So here, in fact, is a distribution of Washington Junior High, the 7th grade boys. And there are 100 in here. Here's the way to read this particular graph. On the bottom, we have the different possible heights, ranging from 53 inches to 65 inches. And the height of each of these bars represents the number of boys who had that height. The boys who were 53 inches tall, there were 3. 1, 2, and then 3 is right here between 2 and 4. There were 5, right between the 4 and the 6. There were 5 boys who were 54 inches tall, etc. There's a total of 100. And I made this chart, so I guarantee you there's 100 of them. So what we did was exactly what happened. We didn't do it by design. We went to do a sample. We took the first kid who came out, and at Washington, it happened to be somebody down here, just as Melissa suggested. It was a kid who was 62 inches tall. So you can see he was a little bit on the tall side for his total group. Over at Lincoln, a relatively similar distribution, not that much different, a little bit of a difference. The distribution is the word for the way the height is kind of spread out over all the boys. So again, some of them are on the shorter side, some of them the taller side. There's a big bunch of them kind of in the middle here. And sure enough, our sample was on the shorter side here at Lincoln. So we can look at these charts in a different way. I can kind of take a look at the pattern of this graph, and it looks a little bit like this. You can kind of see if I do it fast, they kind of almost overlap. And what we're looking at here is called a normal distribution curve. So it's a way of representing the distribution, or the way that different characteristics get spread out over a population. So in this case, the characteristic is height, and height among the 7th grade boys was spread out or distributed over the 7th grade boys in a pattern that looks something like this. A small number who are on the tall side, small number on the shorter side, the bulk in here. And this kind of a distribution is something that we find in many different natural phenomena, not just in the height of 7th grade boys. So here we have a smaller version of those two graphs for the situation we just talked about. Here's the mean for Washington Junior High. It turns out that if you took all 100 that I showed in that first graph and averaged them out, it would be 58.4 inches. And it's the exact same mean as over here. So both schools, the average for the population was exactly the same, but our sample was a little bit different. So in general, the lesson here is that we aren't ordinarily going to measure an entire group of interest. When you read these political polls where they said that, based on a sample of 1,000 plus or minus 3 points, they're making some conclusion about an entire state or the entire country. They're not going to go out and do a poll of the entire country. So we are not usually, for many different reasons, going to sample an entire population. We're going to take a subsample. And it's possible that we could randomly pick people who either represent that population. We could have picked somebody who was 58 inches if they were the first one to walk out, but we could also pick somebody who doesn't quite represent the total group. The higher our, the more individuals we sample, or the more individuals we get the information we want from, the closer, in general, we are going to get to the mean or the average for that group. So this idea of picking at random and the fact that we may or may not be representing the group is really an important one. So let's look at another quick example here. I think everyone, any questions at this point? I think everyone's got the idea. So just to sort of drive the point home, another question: who's taller, 5th grade girls or 7th grade girls? So we sample one 5th grade girl, her height's 58 inches. We sample one 7th grade girl, her height's 56 inches. Our conclusion, based on a small sample of 1, is that 5th grade girls are taller than 7th grade girls. Now, this doesn't make intuitive sense. It's not consistent with our experience. If you got this kind of a study and it went that much against your experience, you'd really want to look at their methods. And in this case, it was a sample size problem. They didn't have a large enough sample. So you're not convinced, I'm going to assume. I think you want to know the same things we did before. So let's take a look at the same sort of curves that we had. In this case, the 5th grade girls, you'll notice the distribution goes from 48 inches to 60 inches. The 7th grade boys, they were taller. The curve looked similar, but they went from somewhere around, I think, 53 up to 65. So similar pattern, it's a normal distribution, but different heights in general. So here, same kind of a thing, 5th grade girls, we happen to sample somebody on the upper end here. It turns out that 13% of this total group would be this tall or taller. Now, how do I know that? Well, I told you there's 100 in here. Well, I didn't tell you. There's 100 in here as well. And if we just count, we see there, of the girls who were 60 inches tall, there were 3, 1, 2, 3, plus 4 who were 59, so that's 7, plus an additional 6 who were 58 inches tall, for a total of 13. 13 out of 100 is 13%. So 13% of this group were this tall or taller. So it's not that improbable that we might sample someone who's on the tall side if we only sampled one girl from the 5th grade class. Similarly, 7th grade girls, the normal distribution looks very similar, but again, these are a taller group. They're going from 53 to 65 inches. Same thing here. We sampled on the shorter side of this group. 20% of the group could be 56 inches or shorter. That's 1 in 5. It's not that inconceivable that you could have made that kind of an error. So here's what we did. We'll put the two groups together. Our graph now goes from 48 inches to 65 inches. The 5th grade girls were here. We sampled from there. If we superimpose the 7th grade girls, we see that there is an intersection here where the two overlap. Makes sense. And we sampled on the shorter side from the 7th grade girls. If we took a larger sample of 30, and if we calculated the mean or the average, we find the 5th grade girls, in fact, are shorter. 7th grade girls are taller. 58 was the average, 54 there. So here is the same graph we just showed with the two means. The mean laid somewhere in here for the 5th grade girls, and it was just a little bit to the right of the 58 for the 7th grade girls. So, in summary, if we only sample a small proportion of a group, the sample size is less likely to represent the average of the entire group than if we have a larger sample. But we don't need to sample everyone, and we aren't going to be able to for practical reasons, and that's the job of the biostatistician. When you're working with a biostatistician designing a study, they're going to consider these factors. This gives you a rough idea of the way they're thinking, and they're going to consider a lot of other technical factors to try to consider what sample size do you need to answer your question, because you're not going to be able to talk to everybody. So, how do we know that our sample is not just a fluke? How do we know that we've got a sample that does represent the total group, and that it's not just something that was a fluke of chance, like getting the tallest boy who came out of the cafeteria? Or another way of putting it is, when do we feel comfortable that our findings closely represent the real situation and are not just due to chance? And that's what I hope to talk about for the rest of the next 10 or 15 minutes. So who's ever heard of the phrase statistical significance or statistically significant? Okay, pretty much everybody.
I made it up.
You'd be a very rich man.
Paul's-
wouldn't it?
Yeah.
Paul's
I
cut.
invented the question mark.
So what does it mean? Anybody want to, what does this mean to you? I'm not asking you to, you're not going to be graded on this, but I'm interested to know what the phrase statistical significance means to you.
Well, I think it's taking all the variables out, that it is driven to being correct. I don't know if that's right, but it's statistically true when you take all the variables out. And I wish you could repeat how you taught that to us.
Okay, others?
So not so much true, but significant due to the actual number of the data presented.
Okay,
Yeah, not true, not true,
okay.
that's right.
So you're backing off of
Oh, yeah,
true.
I'm backing
and,
off on
okay.
true, that's right.
Sarah looked like she might want to say something.
It has the appropriate weight for the population. So it has one of these people represents X amount of people to make it significant.
Okay.
You see it a lot.
Okay, I'm going to let you refine that answer if you don't mind, because I think I'm leading people towards the idea of sample size, because that's really what we were talking about just now, is how many people do you need in a group in order to come up with an answer that you don't think is due to chance. If you can sample everybody, it's not due to chance, but we have this other situation where we can't sample everyone. So let's think in terms of an answer. Suppose you've done the study. Suppose you have found that the 5th grade girls are shorter or taller than the 7th grade girls, and somebody says this is statistically significant. So thinking of it in terms of results of a study as opposed to the sample that you need to get, what is your understanding of it?
So for example, like our stroke rates in Lane County are statistically significant higher than the state average, even though percentage-wise it's a very small percentage difference, but that difference with the small rates makes it I'm so bad at explaining things.
No, you're doing great.
Significantly significant, statistically significant. So it's not always a matter of being 10 or 15% percentage points higher, but it's that difference between the two that makes it stand out. Is this isn't just a randomization? There is really an issue here, or correlation, depending on how you want to look at it.
Okay, that's nicely said. Let's do a little study of our own to try to get at this idea a little more clearly. I'm going to flip a coin. So when you flip a coin, the coin can come up heads or it can come up tails. And the question that we're going to try to answer with this little study, so our study question is the coin fair? So if a fair coin is a coin that one would expect to land on heads and tails with equal probability, or the same amount of times, the same frequency. So let's do our little study, and I'll start with, we're gonna get a bunch of data points. So each flip will be a data point. So it's like getting a person for your pick of the month, or for our heights. Each of these hundreds students was a data point. So first flip, it's heads. So anyone want to make a decision about whether this is a fair coin or not? Anybody have a feeling, yes or no? Okay, you want more data? Okay, so we'll get more data. Heads.
Keep going.
Okay, so
I
you're
wanna
not,
see the coin.
Janet Kay's not convinced.
She's good.
You want to what?
I want to see the coin,
Okay, how do you mean?
like up close and personal. both
Okay,
sides.
okay, and that would be another study design. I mean, if you wanted to examine the coin and you wanted to make a conclusion about whether it's fair, I mean, maybe you would x-ray it and find that it's not weighted properly or something like that. But let's suppose for our purposes, we've designed a study where the only data we get are the flips that I'm doing. Okay, so we've got two, and we had heads and heads. And Janet Kay wants more data. Is anyone else at a point where they want to say it's fair or not? Okay, we'll get more data. Heads.
Oh my God.
Okay, what?
Let's make a bet.
What,
I'll take heads.
what do you mean? Why?
I'll buy you lunch.
Why? Why are you saying that?
Because I would have expected a tail. I mean, I know each one is independent, each flip is independent, but over the long term, I would expect an equal number of heads as tails.
Okay.
So by the time we get 3 heads in a row, I'm starting to think I like that coin.
Okay, are
I
you
wanna
ready
buy
to,
it from you.
are you ready to come up with a conclusion about our?
No.
Okay, and does anyone else want to say, yes, I think it's fair, or yes, I think it's not fair?
I don't think it's fair because you're not flipping it exactly the same each time.
Okay, so, all right, well, let's assume, okay, it's another good point. So what does that point get at?
Your trial isn't standardized.
Okay, right, or it gets at some aspect of the way the study is designed. There might be some bias in the study. Let's assume that I have been doing a really accurate and balanced and fair toss of the coin in every way. Okay, are you ready to weigh in, or do you want more data?
No, because we know that the probability is one. You know, it's just like all those middle school and high school math problems with the flip of the coin. Even if you were to have 10 heads in the row, still on that next flip, you have a 50% chance of getting it.
Okay.
So you could do it 3 times, or you could do it 3,000
Okay,
times.
let's get more data.
Assuming the coin is fair.
Heads.
Yeah, assuming that it's
That's 4 in a row.
Okay, we're at heads.
So,
Anybody feeling like the coin is not fair? If you're feeling like it's not fair, raise your hand if you're feeling like it's not fair.
Or the measurer
Yeah.
is
or
not,
Okay.
the coin may be fair, but
Okay,
the
so
reward may
another
be-
issue. So another issue with the design of the study. Let's assume the study was designed well. We've got 4 heads. I got 2 people raise their hand who are willing at this point to say, I conclude at this point the coin's not fair. Is that?
Yeah, let's
These,
count
okay.
page
Who,
weight.
so raise your hand if raise your hand at this point if you think the coin is fair. Raise your hand if you're willing to conclude that the coin's not fair.
If it was
I
a
had
real
2.
coin,
Okay,
Oh,
it's a real coin.
Yeah, and
But
it's
okay,
hard to conclude
Okay.
when,
based on 4 tosses of heads in a row, who wants to say the coin's not fair?
well, you're not allowing us
You
to
don't have
tell you
enough.
why though. Because your thumb and finger is on it in the exact same position.
Okay, let's
You're
assume.
saying-
Okay.
If you-
Okay, you guys keep
assume
coming
that
back.
100
You keep coming back to study design issues.
Yeah.
For the study that we're doing now, the only data you have is the information about the toss, and we're going to assume that they're done fairly. These are really good points. You always want to question, but let's just assume that these are results you can trust.
assuming no other abnormalities, that everything is 100%
Right.
squarely done.
I just love the way
4
you're.
times is the difference between 4 and 0 is not as much as the difference between 80 and 0. So if you flipped it 80 times and you had heads, I would be more convinced that it was. But there's not enough of
Okay.
a difference between 4 and 0.
5 heads.
Can we see your hand?
You can look at everything after, but right now, let's assume we've got good data. Because the point I'm getting at, you guys, I love the way you're thinking about the design of the study, because there's a reason, I think, that you're questioning the design of the study. But I'm trying to get an idea of your comfort level. At what point are you starting to suspect? I'm getting a lot of discussion, but I don't hear anybody willing to raise their hand except these 2. Is any?
I'm just wondering if, when you call it heads and you flip it with the heads up, if that is making it be heads the next time too. You know
Okay.
what I'm saying?
All right. So
But
are you
he's-
comfortable
he's
with 5 in a
still
row
the
heads?
design issue.
yeah, he
Who's
wants-
comfortable with 5 in a row heads? Who's comfortable with 3 in a row heads?
To say that the coin is not fair.
Yeah, who's suspecting the coin?
5?
Who had suspicions about the coin when we got 3 heads in a row? Raise your hand.
I had
Well,
tossers.
you-
Okay, you voiced it. Okay.
You start wondering.
Who had?
Yeah.
Oh, wait, but
But that
you
doesn't
were
mean
willing to
it's
get more
close.
data.
And you
Okay.
can conclude that. You could say the coin's not fair, but then once you punch the numbers, it's not going to have a statistically significant difference.
At this point.
Okay, we'll
Yeah.
get to that in a sec. So who at 4 heads in a row was willing to say, I don't think this is fair?
well, I have to go there because you're not showing us, you're just telling us.
No, I know. I understand that. Believe me, I understand that point. I understand that there's some suspicion about the methods.
That's a
And-
training on the ethical conduct of research.
Correct.
And if you falsify data, your university can lose lots of grants from things. It actually just happened, I forget, in
Yeah.
Kansas.
No, it's a good point. And I don't take it personally either.
Yeah,
Yeah, don't
we
worry.
couldn't
All right.
see you flipping the coin, and all you did was just tell us.
Okay, so
We had 1 at
6.
4 over here.
1 at 4, I got 6. It's heads. Who's willing to say at this point that the coin is not fair? Okay, pretty much everybody. Now, these are great points about the methods, but let's take a look at this idea. These are the probabilities of getting consecutive heads when you toss a coin, assuming it's a fair coin. If you toss it one time, the probability of getting a head is 1 in 2. So it's pretty obvious. It can either be heads or tails on one toss. And another way of representing that is that it's a 50% probability, or 0.50. It's kind of, writing it this way is kind of the way you would write money, dollars and cents. So 50 cents or 0.50 is 50% of a dollar, 50 cents of a dollar. If you tossed it 2 times, you could either get a head and a head, you could get a head and a tail, you could get a tail and a head, or you could get a tail and a tail. So there's 4 possibilities, and only one of those had 2 heads. So the chances there are 1 in 4, or 25%. We get down here, Jana Kay was getting a little bit uncomfortable at 12.5. So that's about like the sampling we had for the tall side of the girls' distribution. 13% of the girls were taller than that. When we get down to 4 heads, there was a little more discomfort. Everyone was starting to cast aspersions upon my integrity as a researcher. They were saying, this guy's not doing something right here. And there's probably a good reason for that. And the reason was that it starts to feel like an improbable result, probabilistically. In other words, another way of phrasing it, it seemed like a result that was not likely to be just due to chance. There was something else going on here. It wasn't just chance. If it's a fair coin, then probability means more times than not you're going to get an even distribution of heads and tails. But if it was a coin like Carol was getting at, I want to see the coin, maybe it has 2 heads on it. Maybe it's not balanced properly. So if it's not a fair coin, you wouldn't expect to, you might start to see that there's something other than chance at play. There's an imbalance in the coin that's causing this. Because chance alone starts to get really, really low. We got up to 5 or 6. At 5, we were at about 3%. So about 3 out of 100 times, you would expect to see heads 5 times in a row. And that's an important number, as we'll see in a second, between the 6 and the 3, because statisticians usually use 5% for a point where they start to think, this is probably not due to chance. There's a low likelihood, there's a chance of 3.1% likelihood that it's due to chance. We get down around here and we're talking about 7 heads in a row is a little less than 1 in 100, a little less than 1%. So think about this next time you buy a lottery ticket with odds of 1 in 50 million. Let's get back to statistical significance. What statistical significance means is that the probability that the result you have is due to chance is low. So there's a low, the probability that this result, it's kind of confusing sometimes because we're talking about probability and chance in the same sentence. You have to pause for a second and think about it. But your results are not likely to be due to chance when you have a statistical significance. Now, how low? When we say low, well, we choose. Now, when I say we, I don't mean we just decide on a whim that those of us who are going to be working on the particular project are going to pick the value. There's a convention. There's a standard that statisticians use. It's usually less than 5%. So most of the time, a statistician will feel like something is statistically significant when the likelihood that the finding was just by chance and doesn't reflect a real phenomenon in the world is less than 5%. They use something called a p-value, and you'll hear some of your academic colleagues throwing the phrase p-value around. P just stands for probability, actually. So it's just a p-value of less than 0.05, as we see up here, is kind of a standard. Now, so let's go back to our first question, what statistical significance means. Does it mean that the findings are true? As Nancy said, well, no, not really. It doesn't really mean that they're true. It means that it's a matter of the degree of uncertainty, okay? So if it is, if we do 3 heads in a row, we're getting around 12%. That could have just happened. I mean, I've tossed a coin before and had 3 heads in a row. It happens about 12.5% of the time. Okay? So it happens. Could I get 7 in a row? Yeah, I could get 7 in a row. It happens about 1 in 100 times. So if I don't have anything better to do and I just want to toss a coin a lot of the times, every so often I'm going to get 7 in a row heads. So it's not a matter of being true or not, it's a matter of the degree of uncertainty. So does it mean that the study's of better quality? It doesn't mean the study's of better quality. You can have a poorly done study that comes up with a statistically significant result. And in fact, as you all insisted on, there are times when if you have a result that just seems to defy your expectations, you might want to go back and see something about that study and look at the quality of the study. Another idea, another question is, does statistical significance mean that the findings are more important? I think importance has more to do with the real world. So this gets a little bit at what Sarah was saying earlier, and I'd like to just give one final example to drive this point home, and I think something like this might be on your quiz, your survey. So let's talk about 2 different kinds of significance. We talk about statistical significance, and oftentimes you'll hear a researcher or a statistician just use the word significance when what they mean is statistical significance. And it's because they use statistical significance all the time, and it's the kind of significance that they're mostly thinking about. But I want to show you the difference between something called statistical significance, where a finding is not likely to be just a chance finding, and significance that is real-world meaningful, sometimes called clinical significance. It doesn't have to be in a clinic, but it's real-world significance. So suppose we have a program to increase exercise in kids. We designed this program. We have 4,000 participants. So I picked that number deliberately. It's a pretty large number. And as we learned in that first example, when you start to sample 4,000 people, you're not as likely to just get some chance findings. So we have 2,000 kids in the intervention group, and they're the kids who are going to receive this program, and we have 2,000 kids in the control or the comparison group. So before we start the intervention at baseline, each of these groups is getting 60 minutes of exercise a week. So we do the intervention. This was $530,000. It took us 18 months. Everybody was working at it. And at the end of this 18 months and all this money, the intervention group was measured, and they were getting 62 minutes of exercise a week. And the control group hadn't changed. They were still getting 60 minutes of exercise a week. And this was a statistically significant difference. So the difference between this group of 62 minutes a week and 60 was at a p-value of 0.03. Does somebody want to take a shot at putting into other words what this p-value means?
There was a low likelihood that those findings were due to the kids being of a higher income or a different school or that.
Okay, so it's not.
It was balanced.
So there's a real difference. It's not so likely that we actually just asked the wrong kids or got some wrong, where these kids were actually, 59 minutes or 6, maybe they were 60. We believe that they really are getting 2 extra minutes a week. So is that significant? Well, it's statistically significant. We just showed that because it's a low likelihood that it's not a real difference. But is it meaningful to you? Do you want to put $500,000 in 18 months into getting 2 extra minutes of exercise?
Is that all you measured?
I'm sorry?
Is that all you measured?
Well, that's a good question. But to illustrate the idea of the difference between statistical and real-world significance, let's just say that's all we measured. So the point here, though, is that just because something is statistically significant doesn't mean that, we have to act on that now or we have to do something about that. It's a measure of the probability of your findings just being due to chance. But you still have to weigh it against the real world, and most people would probably say this was a program that we don't want to invest in. So, some implications for study design, something Susan talked about.
Just in terms of the prior slide, you are using the phrase clinically significant, which I think for community-based programs is not really a relevant phrase. I tend to think of it as practical significance.
Perfect, a great term.
So, yeah, in that case, there was clearly a statistically significant difference, but practically, who cares if it's increases their exercise by 2 minutes or not?
Yeah, a
So
good point.
Just the practical significance
Yeah,
helps me.
and I like, and another alternative term is real world significance. Is it significant in the real world of what you're going to be doing? Yeah. So, as Susan alluded to, there are some implications for your design of your study that have to do with these ideas of how do you sample, who do you sample, how many do you sample, and this gets built into the question that you're going to ask. You need to work with your statistician when you're doing it. So, you need to understand how large or small of a difference is important to detect. Do you need to show more than 2 minutes a week? If so, you need to try to make that clear, because your statistician can tell you how many how large of a sample you need to show that size of a difference. And then finally, how many participants do you need? So this cartoon, the man is saying, with this much grant money, the only experiment we can do is flip a coin. But I think you guys can do more than that with the money you have here. And I'm hoping that, in some ways, I hope that this presentation opened up more questions than it answered, because there are a lot of other unanswered questions about this sort of thing. But mostly I hope it'll make you feel a little more familiar with these concepts and more comfortable talking with your academic partners when you design your studies. So good luck.